All right, if you're building anything with AI these days, you've got to get your head around LLM embeddings. Seriously, it's not just a nice-to-have anymore, it's pretty much a non-negotiable part of your toolkit. So let's dive right in and figure out what's really going on under the hood.
Okay, let's start with a classic problem. I mean, every developer bumps into this. You've got two sentences, right? I sat by the river bank and I opened a bank account. Now, for you and me, it's a piece of cake. We instantly know one bank is about a river and the other is about money. But for a machine, it just sees the same four letters, B-A-N-K. So the big question is, how on earth does an AI figure out the difference?
Well, the answer is pretty cool, actually. They build what you could call a mathematical bridge. And what this bridge does is translate our messy, nuanced human language into the clean, structured world of numbers, something a computer can actually understand. And that bridge, my friends, is built using embeddings.
All right, so let's walk across that bridge. We're about to see how this fuzzy idea of meaning gets turned into something very concrete, a vector. This is where the magic happens, where words literally become math.
So what exactly is an LLM embedding when you get right down to it? Honestly, it's simpler than you might think. It's just a list of numbers. Yep, a long list of numbers we call a vector. Think of it like a unique numerical fingerprint for a piece of text, whether that's a single word, a full sentence, or even a whole book. It captures the very essence of its meaning and context.
But here's where it gets really cool. It's not just about the numbers. It's about where those numbers place the concept on a giant meaning map. Just imagine this huge invisible map of ideas. On this map, things that mean similar things are neighbors. So you'd find dog, puppy, and canine all hanging out together in one corner, while spreadsheet would be, way on the other side of the map.
So let's break this down. First, you have the vector itself. That's just the list of numbers, right? The raw coordinates. Then you have what's called the semantic space. That's our big meaning map where all these concepts live. And here's the absolute key. They're context-aware. This is how we solve our original problem. The model is smart enough to know that riverbank and bank account are totally different things, so it gives them completely different vectors, putting them in separate neighborhoods on that map. Problem solved.
Okay, so this is great. We've got these numerical fingerprints, these coordinates on our meaning map. But so what? How do we actually use them to see if two ideas are similar? How does a machine measure that distance?
And this is the key insight, right here. We completely stop looking at the words. Forget them. It's all about the vectors now. And we don't measure similarity by counting how many letters they share. No way. We measure the angle between their vectors. If the angle is small, they're pointing in roughly the same direction on that meaning map. And that means they're super similar in meaning.
Now, the math behind this is called cosine similarity. And don't worry, you don't need to dust off your old trig textbook. All you need to know is what the score means. It's super intuitive. A perfect score of 1.0? That means the vectors are identical, pointing in the exact same direction. The meaning is the same. A score of 0? That means they're at a 90-degree angle to each other, totally unrelated. And of course, everything in between tells you just how similar they are. It's a really elegant way to put a number on meaning.
All right, enough theory. Let's get our hands dirty. As a developer, how do you actually make these things? Well, you've basically got two main options. Option 1, you can run a library right on your own computer. This is awesome for privacy, for just playing around and prototyping, and hey, it's free. The downside, it uses your own computer's power. Option 2, you can use a big-time production API. This gets you the best accuracy and it can scale like crazy. But you've got to think about network lag, and of course, it's going to cost you money. Let's check out the code for each.
So here's option A, doing it locally. We're using a really popular library from Hugging Face called sentence transformers. The important thing here is that all this code runs right on your machine. Nothing leaves your laptop. And check out the sentences we're comparing. The developer is debugging the code versus a programmer is fixing a bug. I mean, they're basically saying the same thing, just with different words.
So what's actually happening here? It's pretty straightforward. Step 1, you grab a pre-trained model. Step 2, you give it the sentences you want to compare. Step 3 is the magic part. Model.encode turns your text into those number vectors. And finally, step 4, you calculate the similarity score. Boom, done.
And check out the result we get, a score of 0.85. That is really close to 1. It proves the machine gets it. It understands that a developer debugging and a programmer fixing a bug are pretty much the same thing, even though the words are different. That right there is the power of embeddings.
Okay, on to option B.
Using a production API. This is the route you'd take for a real scalable app. Here we're using the OpenAI API. And look, the code is just as simple. The big difference is you're not doing the work on your machine. You're sending the text over the internet to a massive model, and it sends the embedding back. And when you get that vector back from a powerhouse model like OpenAI's, just look at the size of it. We're talking 1,536 numbers. That massive size, what we call high dimensionality, is what lets it capture all the tiny, subtle details in the meaning. It's why these big API models are so incredibly accurate.
And just like that, we've come full circle. We started with that bank problem and this idea of a mathematical bridge, and now we've actually walked across it. We've seen how you go from a fuzzy concept to a list of numbers and then to actual Python code that can measure meaning. It's pretty amazing.
But hold on. Generating 1 or 2 vectors is cool, but it's really just the beginning of the story. To build something really useful, like a search engine that understands what you mean or a RAG system, you're going to need to deal with millions of these things.
And that brings us to the big, final question that every architect has to face. Okay, great. You can make millions of these vectors. Now what? Where do you put them all? And more importantly, how do you search through all of them like instantly to find what you're looking for? Well, that's the problem that vector databases solve. But that, my friends, is a topic for another day.